Okay, problem 9 asks us to plot thermal efficiency and mean effective pressure versus temperature for 3 different compression ratios. And this is for an Otto cycle. So I just drew the PV diagram to remind me about this process. Process 1 to 2, isentropic compression. 2 to 3, constant volume heat addition. 3 to 4, isentropic expansion. And 4 to 1 is constant volume heat rejection. Okay, so here's our equations for our thermal efficiency and our mean effective pressure. Okay, so our state 1 is fixed. It's given us our P1 is equal to 14.7 pounds force per inch squared, and T1 is equal to 530 degrees Fahrenheit. And the temperature that we're going to plot against is the T3 is going to range from 2,000 to 5,000 degrees Fahrenheit. And our 3 different pressure ratios that we got to calculate for are 6, 8, and 10. And our specific volume for the state 1 can be calculated using the ideal gas equation here very easily. And there's my work. Not very difficult. Okay, so state 2 is going to be defined by the different pressure ratios because state 1 doesn't change. And so we know our specific volume sub ratio is going to depend on our compression ratio here, because the specific volume of ratio of 1 isn't going to change. State 3 is going to be defined by the temperature. And since all this is air acting as an ideal gas, all we need is temperature to calculate our specific energy and enthalpy. And so VR4 is going to depend on the temperature and the compression ratio, as we can see here. Because as the temperature changes, so does V, the specific ratio, or the specific volume of the ratio at state 3. And then state 4 will be defined by the specific volume also. We can find the temperature and the specific energy, internal energy, and enthalpy. And then we have our heat transfer into the system between states 2 and 3, just is equal to the internal energy at 3 minus internal energy at 2. And then the heat rejection is just equal to the internal energy at 4 minus the internal energy at 1. And then of course we know the work of the cycle is just equal to heat addition minus heat rejection. Using Excel, you can plot these, and we see that for a larger compression ratio, you're just going to have a higher thermal efficiency, and for the varying temperatures, at the lowest temperature, you tend to have the highest efficiency. And then our mean effective pressures, those lines all cross right around in here about 3,200 degrees Fahrenheit. The problem asks us only to plot thermal efficiency and mean effective pressure versus temperature for our three different compression ratios. So there's the graphs.